Name's Owein Reese. I work for MediaMath. We are an ad tech company. Yay. We gave you pizza. We're big in Scala. We like other languages too. We are actively recruiting. Big data, big throughput, lots of requests a second type of deal. So we've got a lot to offer. Dependent types in Scala, awesome. So I've seen a lot of presentations where they talk about dependent types and they say Scala has them. And unless you've been to Miles Sabin workshop, I haven't really seen something where you can actually use, or how you would use, or how you would try and incorporate this into your Scala code. So eventually I'm going to hit you up with probably one thing you probably thought types could not do for your code. And then I'm also going to hit you up with how to do compile time proofs. That is, prove something at compile time about your application or about some data structure or algorithm that won't let the compiler pass if it's not true. But to get there, to get to that level, first we're going to have to talk about some sort of building blocks, some sort of techniques that we're going to need, or thoughts about how to work with types in Scala, specifically with the dependent types. And after each section, I'll pause and I'll let you guys, ask some questions and that sort of thing. But as this talk is geared at intermediate level or above, and to keep things moving at a reasonable pace, because I don't want to stay here until 11. I'm sure these guys want to get home too and see their loved ones. I may not be able to answer all questions, so please feel free to hit me up afterwards, and I will stay as late as I possibly can for any questions you may have. So, with that said, what is a dependent type? You saw this thing, you'd never seen this before, you probably Googled it and you thought, awesome, there's these cool languages called Coq and Agda and Idris, and they have this wonderful thing where they mix sort of propositional logic in together with a type system, and it compiles and they get these formal proofs right in their type system. It's awesome, it's great. Scala does not have these, so please, if you do put it in dependent types with Scala, you can get there, but it's kind of hard. So what Scala has is something more along the lines of a path-dependent type. So here's a good example. I've got a type v, some val defined in that type v on this trait. I pass that thing in, and what comes out is a type that depends upon the value that was passed in. What's that? Can I make that larger? No.
Smaller.
Probably not either. This is sort of like just an example case, but if we were to make something with this dependent type, we do make one, make two, and we put it to vals, I don't even need to tell the compiler that this is an int or that's a string. It will know. Those types will be there, it will be reified right at compile time, and it will know. So even though magic has a return type, that type is changing. You may also see some other forms of these guys. Here's class bar, the method called do nothing with bar. You'll see this kind of thing in the cake pattern. Cake pattern is like a whole nother talk in and of itself, so I'm going to just show you this. Essentially what it does is this B2 is path dependent upon where it originated from. So this bar and this bar type are actually not the same thing. So if I pass B2 into the F1 do nothing, it's going to tell me that this is not the right bar, even though they essentially look like the same sort of thing. This is actually here, it exists. We're not going to use this for the rest of the talk because you can't really do too much with them. So we see this kind of thing in the standard library. It actually does exist. Yes?
Sorry, I apologize. Is it possible to try to zoom in to the actual
Can we zoom in?
Command plus.
What's that?
Command plus. Command plus.
The thing that looks like two inverted.
Oh, awesome. Whoa, yeah. Very cool. Is that better? I'm sorry, I'm a bit of a Mac newbie here.
Can you make the logo smaller again?
All right, so No, these really do. These exist in the standard library in Scala. As you can see, 2 different developers made these up. You can tell one's a def, one's an actual val that's a function. If you go look in the standard library, these are there. You can use them. You can see them. And they actually have some a pretty good use if you want to go to them. And I'm about to show you, we're going to build something very similar to this. I'm going to show you how these work and why they might actually exist. So let's do a simple first example. I'm going to build a type class. Actually, I'm going to build a type extractor. The idea here is I'm going to pass something in, which is a higher kind of type, with something nested in. So let's say we have a list of int. And I want that t to actually be int. So this f can be list of int, that type can be int. And I do it just like this. And I've set this up in a very sort of special way here. So this implies actually important. This applies sort of like your summer. This is how you form sort of an escape hatch into an object. When you have an object, you can put as many implicits as you want in it. You can put all sorts of classes and all sorts of boilerplate and goop that you don't want anybody to see. But this apply, the way I've set this up, when the compiler goes looking for a type of inner of your f, it can actually find it here without having to do inner dot underscore. So that way, you can put all sorts of stuff, like implicit conversions, those evil little things that like always screw you up, in here, and no one will see it. This is just, this is your simple def, like here's an f, here's an a, f of a, or list of int, a is your int, and boom, it works. It's great, I've got this. So, this is kind of useless. It doesn't do anything. So we can make this a little bit more practical. Let's add an apply method to something, and let's be more specific. Let's do is future. So I'm going to have a type t, the type of the future. I'm going to pass that f in, and I'm going to get out a future of t. In other words, this is a type-safe conversion function. Like I'm casting at a type-safe way. Right at compile time, it will know. So again, nothing's different about this. I've just put this in, and if I want to go use this, I can use it as an implicit guard. So, like if you have something like list, you've seen like sum or product. Sum only works if something is numerical, or like list.order only works if there's an order of the type A. So I can put this in, and this does something really weird. This signature is odd. It's isf.t. This is my dependent type, and an appended type, or even the abstract types, they're just types. I can put them anywhere. I can put them as a type parameter in here. So I get this thing in this very abstract type, which the compiler can't tell you, like, does this have a map? And I can put it into this thing that I created, and out comes a future, which the compiler can then say, oh yeah, futures, these have maps. I can map over this. I've got this, I get it out, I pass the thing out, and boom, it's a future of this type. And it works. So a couple of the things that I just went over before is, like, use a companion object. Use that, put that apply in, let that be your sort of escape hatch, your peek hole into the world of where you're going to start building this stuff. You can shove as much boilerplate in there. No one will see it. You want implicit types, you want weird casting and that kind of stuff. There it is. You can use dependent types as type parameters, and these dependent types can allow us to sort of cross that type boundary that the compiler might complain about unless you did is-a or some dirty, ugly casting. Questions? The signature of inner, you're sure the answer is yes, but?
Right. So why is T in abstract type?
Why T being up?
Yeah, why does T need to be an abstract type member as opposed to a type parameter?
So why is T an abstract type parameter rather than some type member? Because this is a toy example I'm just doing for demonstration purposes. I mean, yeah, you could do it as a type parameter, but one of the nice things about dependent types is as a It's a very nice friend of ours, Adam Klein, once said, you know, you look at some of this stuff and you get what you would call type soup. That's like 15 different type parameters going out this way. If I just want to deal with one type, I've got it. There it is. And I can get access to all the other types right on there. But yeah, this is a toy example. It's just sort of demonstration purposes. You wouldn't actually want to do this in your real code. Anything else? All right, cool. So let's capture more than one type. I mean, inner's like my list of int. So I've got t here. Now I want to sort of get a little more general case, like we did for future. Now let's do for any sort of type here. So I've got my type w of x, just a type constructor here, and I've made everything the same way I did for its inner. The only difference is this type constructor here and the return type. It's kind of funny because we have this x parameter here and we don't have x listed anywhere else. Let's talk about a little bit of an aside. So it's not really a type constructor the way we have it listed. This is more like an equation. So we have actually a number of valid ways we can declare this. The first is, of course, the way we did. W of x is f of x. So that x is actually, if you think about it, it's a variable, some type that I can put in. And it works just like a variable. We can actually ignore that x completely and just give f of int. And in that case, I've sort of formed a type level closure around f, because the thing I might expose from my dependent type is this ignore. I wouldn't see f, but f does appear in the return type that I get out. I can just return x. Yes, it's a higher kind of type, but I get a non-higher kind of type out. Or I can ignore it altogether and just be like, hey, this is what it is, deal with it. So when we have these things, we often call them, or we can put in these things called type refinements. And this aux, and I've called it aux because the canonical library of like learning some of this stuff is shapeless, and he calls aux pretty much everything in shapeless. So when you go looking for a library like, like, hey, I want to see some more examples, that's where you're going to go, and you're going to see these aux. So here we are. This is called technically a type refinement. So what it is it's my parameters. And the way I've defined this, if you want to talk in a mathematical sense, is that this is a one-to-one and a onto mapping. So in other words, you have one parameter to each. That means this is inversible, or it has an inverse. Well, that's a really fancy way of saying this is an alias. Like this is an alias to all of that junk. So I can go this way and say aux of list of int list, and it's this, but I can also go this way and get back my aux. This is important. This is gonna sort of unlock something for us, which you're going to be using a lot when you start to do this kind of stuff. So Scala, the compiler, can only capture or can only calculate one type. So you get one free type parameter. So your can build from, those sorts of things on collections where you see like, two of the parameters defined and this out parameter that you get, like it's not defined anywhere. Well, Scala can calculate that for you. But only one of them. You try and supply two and it's going to look and be like, okay, any. That's what it is, any. That's what you get. Here I've got three. I'm passing in one parameter. I've got three over here. And this is the funny thing. So dependent types are deterministic. If I were to pass in list of int, the only thing this f could be is a list. The only thing that a could be is an int. We know this. Right at compile time, we've declared this. You can't do any other way because Scala is going to try and infer the least, or the greatest lower bound, I should say, or least lower bound, or whatever. It's going to go right down to list. List and int. It's not going to be like it's a traversable of int or anything like that. But because I've declared the variable here, I can't do a part.w and a part.t here because that won't compile. I don't have access to it at this scope. I have access to it here, and I've got access to it here, but not in here. So if I want to be able to use these things and use these types, which I am essentially capturing and pulling out, or extracting, if you will, I need to use this aux parameter. But then I can use those type parameters to actually put constraints on this thing that my parameter here does not. So if you guys aren't familiar with Scala Z or Scala Z, however you want to pronounce it, functor is just anything with a map. So like option set list, anything that has dot map on it, that's what functor is. And monoid, that's just anything with an operation and an identity. So I'm going to say like int a lot. Think addition and 0. A plus 0 equals A. 0 is your identity. So let's see 0 here. So what this would do, with this thing here, is I'm going to pull this apart. I'm going to get this thing into list of int. I'm going to map over it, so list.map, and all those things will be 0. So if I have list 1, 2, 3, I'm going to get list 0, 0, 0. And that's what this would do. This will do this for anything that can be pulled apart, for sets, for options, for anything of that sort of nature. So when you're dealing with these kinds of things, you don't have to have just one abstract type in your traits. You can have as many as you want. Scala's can give you as many types as you want. You can fill them all up. They lifted 22, right? They lifted 22? Yeah, 22 or more. You can have 50 million abstract types. Please don't. You can use these type refinements to recapture these types, to sort of pull them out and use them within the same scope of your function that you might want to do. And then they don't count as free parameters. I can still have one additional parameter, which is like open to Scala calculating it. Sometimes I need that, and that example I really didn't. And then I can use those types that I've sort of pulled out, I can use those to put constraints on the rest of the function. Also, it's strange, but sometimes you ever deal with you have like a types, you have a function, it goes in, and you want to call some other function down in that class, but it's got an implicit that it requires. And you're looking at it going, it is this type. Ints are ordered. Come on, just work, just figure it out. And Scala's looking at you going I got this type thing. I don't know that this int is ordered. You can use these to sort of get back to that and say yes, this really does have an ordering, and I want to call it on some function within my function, and the implicit gets summoned, and everybody's great and everybody's happy, compiles. Any questions? No? So far so good? Awesome. Wow, that's pretty cool. All right. So let's start doing a compile time. Oh, sorry, you had a question? You have a comment to address what Chris was saying earlier? Okay. So type parameters versus type members. All right.
And the way you just worded what I was thinking about context bounds.
So you're thinking about context bounds.
Yeah, so that's kind of one example where you're limited to one parameter. You can't have a context bound on one parameter.
You can't have a context bound with the wrong parameter. Maybe, yeah. I mean, thank you for actually saying something like this. Yeah, these abstract types, you guys can put any sort of bound, context bounds, that kind of stuff. But these abstract types, you can have lower bounds, upper bounds, any sort of constraint you can generally stick on these things. You can sort of get away with these guys, which is actually really, really, really useful. It's great that I showed you that what we use in the cake pattern, and you have this nested class, and everybody's happy, la la la. Oftentimes, you want to have some sort of bound. You want to have some sort of bound on this, like this extends this type, because that actually helps you to solve certain things, or to infer and force things in these type constraints that you might develop. Anyone else? All right, cool. Oh. All right, so type level if statement. So I'm going to take this magical apply either, and I'm going to show you how to build it in a second. But what we've got is we've got some argument going in here. I've got two functions. One's an int to an int, and the other's a double to a string. If I pass in an int here, it uses this function. If I pass a double, it uses this. These are not partial functions. These are actual functions. There's no or else being mapped underneath here. I'm actually straight up using a function. And at compile time, it's going to figure it out, and it's going to send out the right type, we can assert these values are the same. So the setup sort of looks like you would with any sort of implicit parameter. I'm going to have some type t and a function f and a function g. I've made them as about as abstract as I can. You still guys having trouble seeing? I see some squinting eyes. So yeah, that's not helping. All right, so we also have this out. So my dependent type, I am telling the compiler, or I am hinting to the compiler that it is going to be the dependent type coming out. Sometimes you have to do this. As awesome as Scala is at type inference, sometimes if I don't do this, for these kinds of cases, what I get is an any, or an any ref. It's really not helpful because what I'm trying to do is I'm trying to have real types. So I'm going to set up this trait much the same way as I did with our explicit type converters. I'm just going to set up a 3-argument function, have my type out, and I'm going to go to town. And it looks like this. So again, I've got my apply. I apply the same thing that opens up the world to everybody, lets me use this without having to do eapply dot underscore. And then I've got this implicit def f apply. So what this is going to do is I'm going to look for a t to r, which matches this t right here, put it in, call it, and the output is r. So if it hits into here, if I pass an integer and I've got my integer function int, it will hit this, it will say yes, this is this, call it, and out we go. If not, I'm going to go down to here, and it's going to look at the second function. If it can't find any, it's just going to give you a compilation error. That's the best thing. But if it doesn't, it uses one of these. I set this up in a sort of special way where I've got a trait and an object. And this is not because I'm just trying to, piece these things out. So let's play devil's advocate. If I were to pass in an integer, an any to string, and an any to string, the compiler would look at this if these were both in this object, straight up without this trait, and would say, these both work. I don't know which one to use. Both of these implicits are valid. You tell me. Sorry, I'm out. This, on the other hand, uses implicit resolution order. So in other words, I am telling Scala to first look at this, and if this works, use this. And if it doesn't, via implicit resolution order, I will now step into this trait, and I'll then look to see if this one matches it. So here's where we get the if statement, this compile time if statement. If this, use it. Else, use this guy. And it magically works.
So does that mean that if you pass in that any, you will use the second one?
So this means that if I pass in any, it will use the second one. What it will do, so let's say if my first argument had some type of any. I don't know how you get that, but let's suppose that we have a type of any as my first argument. It's going to use the very first function here because any will pretty much fall into this, right? No, it won't. If I have int, it'll go, this is an any, I can't compile. Sorry, if this were an any, yes, it would use it. So, yes, so it's going to use the first one that matches. This one first, then this one. Sorry, next question, Brian?
How far down the trait linearizing will it go? Can it only do if else? Can it do if, else if? Like how far can it go?
So your question is, how far down can this linearization go? Can it do if else or if else, if else, if else, if else? If else, if else, if else, if else, if else, as far as you want to go. I've never pushed the bounds or the limits of how it is. I'm sure it's something like 64,000 something or whatever, which happens to be like the top bound of the Scala compiler and number of steps you can step through when trying to type things.
How would you define that? Just more traits?
How would I find more traits? Yeah, more traits.
Okay.
And just sort of tack them on. So, sorry, you had a question? No? Okay. So we're sort of pattern matching on types here with this if else sort of statement. We're looking for the type that matches. If it does, use it. Else, use the next, and so on. We're going to take advantage of this implicit resolution order to avoid implicit ambiguity. In other words, if I have two functions of any to something, and I pass in damn near anything, I want it to just use one of them, and the first one that's in the object is the one I want it to use. And then we're going to make sure that we pass out that dot out, or that dependent type, as the output, just to remind the compiler this is the type that it should be coming out. Otherwise, sometimes, in the most frustrating ways, it will give you an any or an any ref, or some weird ass type. So we have an if-else statement. We can have a loop at compile time as well. So we have this foo, and it's got a type v. If we have foo of 1, this won't compile because there's no monoid for foo of int. There is for int. We do have a 0 for integers. We don't have a 0 for foo of int, unless you yourself go out and define one. I didn't. So I would like this to work, but I can't with inner. So let's make another type class, just like inner. But what I'm going to do is I'm going to take advantage of the fact that there is a structure within my types that allows me to iterate. And the fact of that is I have a foo, which is a type constructor, and inside of it is another foo, which is a type constructor with an int. So I have type constructor, int. And I'm going to recurse over these guys. So, before we even try and get into this, when we're constructing a recursive algorithm, what do? We have our arguments that go in, and we have our accumulator. And we have some condition that truncates this recursive looping. We have, if condition is true, return the accumulator, else, some new arguments plus whatever I've changed to my accumulator. And we're going to run that way. And that's essentially what we're doing here. Here's my unwrap. Again, I've got my lovely apply. So I've got all this stuff nested in. The world never sees it. It just gets out right here. And I'm going to get to this one in just a second. This is the same as inner, right? I mean, it looks, this is the exact same thing, like f of a and my f of a and int. So if this is a list of int, f is list, a is int, and everything works. This guy that gets kind of weird. So an implicit def, it's just a function. And functions can have implicits. The only difference here is I have made a sort of recursive definition. So I've said if this g itself can be unwrapped, then make it. Choose this one first. So this foo of int will hit here and it'll go f is foo, g is foo of int, and that can be unwrapped. Can't be unwrapped here because I can't unwrap int any further, but I can drop down through implicit resolution order to this one, and it'll be foo of int. My inner type, here, this type parameter, this dependent type, I am actually using this to pass the type that I get here all the way back up through every single iteration. This is my accumulator. This is like my variable which I get to use to pass that information along through the things. So if I go in here, int, it's always dependent, always dependent, always dependent until I get to int. And this is magical. This kind of has a lot of people, when it comes to dependent types, getting excited about this fact that this inner sort of acts as a bridge between each of the implicit scopes, at least at the type level. So if I do it this way, again using my aux to get to the A, to bound my type on monoid, I get out 0. And notice I've said inner.t. That's very important. Just to remind the compiler that yes, the type I want is the thing that's nested in. So I've got foo of 1 and I get out 0 because that's what I'm looking for. Awesome. Wonderful. So the big deal, the big thing, the thing that gets everybody excited is that dependent types can be used to pass type information along at each step of your recursion. We can have traits which are defined in terms of themselves, but with slightly different types. And we can use that form a looping structure as long as there is some sort of structure to my types to allow me to loop over this. In this case, we had types defined within types as the type parameter, that sort of way. If we had some sort of mechanism where we had a shapeless H list or something like that, we could recurse over that way too, because the types form a list. There's all sorts of ways to recurse over. Anybody have any questions? What's the practical use of this? Wow, did you see this? Because you're about to segue right into the next segment. Anybody else got another question before I go to the next segment? And try and blow your minds. Because when I got shown this, wow.
Does it make the compilation slower?
Does it make the compilation slower? You better believe it. You like your compile times? As I go, I hit compile, I get my coffee, I add my milk, I taste it till it's ready, I go back, I sit down at my computer, it's great. You add this stuff in where it's recursing, you can go down, you can make some toast, you can butter it, you can make your coffee, you can pour, you can have it, you go back, you have a conversation with your friend, you come back, it's still going. You get on a chair, you have a nice sword fight like XKCD style, and then maybe you can sit down and it's going. So, yes. All right, let's do something useful. Who likes to write this? This is a future list of set of int. Maybe I've done a database call. I'm getting a list of all the sets of the IDs of all my users that have some sort of order or something like that. And I just want to do a function on that int. So I have to call that map of f. And there might be a whole different bunch of these guys, all these different things, all these things which are essentially functors that have a map. Wow, what a pain in the ass. Let's define a nested mapper. Let's make our types map for us so that we don't ever have to write another map again. This is very similar to what I did before. I make an implicit right here. This guy, I could call it anything. This isn't important. It just has this nice, lovely def. Mapper.out. Remind the compiler, this is what you're going to be getting back. Now my trait, my mapper. Here's B to C, and here's some type A, and I'm going to call it out. The reason is I don't know how far down the recursive level I'm going to go, so I'm calling this B, not A. And I'm just going to pass that function along. So how would I do that? All right, there's a lot on this slide. Huh. This is going to be the most gnarly slide you see all night. So let's break it down. First, I have my lovely apply. This thing that opens up the world to the rest of the guys, and I can put all the stuff that I want in here, and they'll never see it. It's lovely, it's great, it comes out. Next, we have our base case. Notice that this base case is at the same level as our object mapper. I haven't sort of done this as a different trait which it extends, because I would like it to short circuit at the first instance. If you were to put it in a trait, it would go down. So if I had some function of list of any to something, I pass in a list of int. If I put it in as a trait, it would go all the way to the bottom, which is great and wonderful, but I might just want it to stop at the very first list, because a list of any is a list of damn near anything. So I'm going to put base here. It's just an f of a, my list of int. B will be something which is bounded by a, so say int, and C is what comes out. Maybe it's another int. I'm mapping on this. I'm just adding one or turning it to 0 like I've been turning everything else. Everything goes to 0. Awesome. Fmap is a functor. So it's just, if this is a list, it's calling list.map, turn this to 0, or however this function is going to be defined. Call that function map over it. This is very similar to what I did last time. So there I was only trying to calculate or solve for a type and pull it out. This time I'm actually trying to get it to do something with it. I'm actually trying it to call a map. So I'm using this this mapper here, which is, again, the same sort of thing. It's a list of something. Here's the list, and here's the inner list of whatever the hell else is in there. Right into there. I'm going to call this nested mapper. pass it as parameter, give my function in, and let that function just float all the way down along the implicits until I get to the point where it actually matches and defines, and then I'll call it and pull it back up. Nested dot out. It's just a type parameter. Here's my f, maybe it's list. Nested dot out is the product. If I have an f of a to b on my list of ints, let's say it's int to string, I'll get out a list of string. So I need to tell it what this out is going to be, and essentially it's this. Sort of passed up and accumulated with each different sort of thing. So if it's a set of list of set of list of set of list of, then it goes right into here and I get this thing out. Any questions before I move on? Because if we run this, if I give you a list of 1, and I just want to add 1 to it, and I put that assert, it works. It's wonderful. It's great. What's the problem with equals in Scala? Anybody? Anybody know? You get this from Java. It calls dot equals, which is defined on any. It doesn't type check. Oh, that sucks. It's telling me it's this weird mapper of list of int, some out parameter. Why is this? Why is that the case? Because here, when it's doing type inferencing, it's saying, oh, some mapper of some abstract type out. That's what the type is. I don't know what it is. Somehow it knows it's a list of int, at least at the value level, but it's completely and totally lost the type. But remember those type refinements that I showed you before? That thing which allows you to get those types at your implicit scope? Well, I can also use them to hint to the compiler and tell it, hey, by the way, that dependent type, this is what it is. And now that type inferencing can go in, it'll check it and go like, oh, yeah, okay, that's the type. That's awesome. Yes, it really is a list of int. And then that identity will actually work. It won't give you a compile time error. And you will have a reified type all the way to hint, as reified as Scala gets. At compile time, not at runtime. So I can recapture, I can get back to the thing that I wanted to get back to. I've sort of left the rest of this out so you guys can see just what's important. So I get the mother of all abstractions. I can do this called map. I could use a monad as well at the bottom, and I could have map all the way to flat map, just changing the base case. Type inference. Okay, look. The Haskellers will look at you and say like, oh, if it compiles, and if it type checks and compiles, it must be right, right? You ever heard that? How many of you have heard that? Yes? No? Okay, look. Less than, a to bool. Greater than, a to bool. Totally different meanings. So that's a little bit bullshit. But what we get with not having that sort of, with having a weaker type inference of that, is we get dependent types. We just have to sometimes help the compiler figure out what those types are. And we do that by using type refinement. Any questions? Have I lost? How many of you have I lost by now? Nobody? Okay, where did I lose you?
Just the beginning, but
At the beginning. Oh, great. Okay. So, the next section is probably what you all came for. We're going to use our types to prove something. So if some algorithm or some data structure has an invariant, and that invariant can be codified at the type level, we can use those types to put a constraint on that algorithm, a constraint that the compiler will adhere to and will blow up in your face if you don't. This really is, if it compiles, it's correct. So let's make a balanced tree. You ever do the AVL tree back like when your algorithm's 201 and like they're like, here's CLRS and for assignment you're going to do AVL tree. What is an AVL tree? Well, the right side or the left side must be equal to the height or one different than the other side of the tree. In this case, I'm going to be a little bit more restrictive. I'm going to say the left side of the tree is going to be greater than or equal to the right side plus 1. 0 or plus 1. So I'll just have this sealed trait. Subject leaf, extends tree, kind of looks like nil on list. And then this trait branch, which has a left and a right, a tree, and a value t. And I've got this weird thing here. So this is a nat. It's a natural. I'm stealing this from Shapeless because Shapeless has some really nice and wonderful things. And rather than me try and re-implement them, I'm just going to use them. Plus, it's also a plug for Shapeless, which you guys should definitely take a look at. Awesome. So it gives me some certain things. So what is a nat? A nat is just a type level integer. But it's more than that. It's a natural number. So it's 0, 1, 2, 3, everything 0 or greater as integers. Those are natural numbers. So I get a couple of things out of this. I get a type level ordering. So less than or equal to. I get multiplication, division, summation, power, and I also get this really nifty thing called diff, where if the left is greater than or equal to the right, it compiles. And only if it's less than or... Wow, I could use that for my tree, couldn't I? And this is the proof. This simple little basic thing is my proof. This is it. This is the magic. Remember, it's a sealed trait, so if you want to make a branch, you have to call my apply. I have restricted that. You're a universe down. Like, here's your only way to get it. Therefore, no one can come along and sort of circumvent the compiler and just make one or extend one or something. This is it. So, here's my value. Here's my two trees. And dot n. That's the height. I probably should have called it dot h. So here's dot n, dot n. This diff, this aux is going to tell me what the difference between these two numbers are. And it's going to calculate that out using an aux and produce this d, which I capture. It's my dependent type, which I'm going to capture up here. So this is not a free parameter, but this d is bounded by a nat, so I have to also bound it with a nat up here. And then I'm going to pass it to this, because I'm using my dependent type to force constraints on this stuff. So this d must be less than or equal to 1. And suck is successor. That means just add 1. Because I mean, if I have a tree of height of 1 and a tree of height of 2, and I'm building something on top of that, it's going to have height 1 more. And I get my branch out. And this, at each and every stage, is going to force each side, or the left side, to be 1 higher or equal to in height the right side at every step. That's it. Compile time proof. Done. And it works. If I pass this in, this will work. And this part won't, because this is way higher. This is like 2 greater, because that's at height 2, and this is the left side's lower than the right. So that's kind of really restrictive, right? Making this left side, right side type of thing. I kind of want a more general. I want to have a compile time verified AVL. But unfortunately, the way I define this apply, I have, in a sense, restricted myself, because I can't put 2 applies here with implicits, because the compiler will just yell at me. If I try and do this with traits and use some sort of implicit ordering, well, the one apply may overwrite the other, or you might get some weird compilation errors or something. So I can't exactly do this in a direct way. I have to do this in an indirect way. So I'll use an indirection. I'll just make another trait, and I'll have that depend on it, and this trait will call this stuff. And I'll pass the height that's calculated from my tree builder in, pass it as the aux, and I'll have this lovely tree that just is doing essentially what my apply did way back up there. And I will define it the same way I've been doing before. Some low priority tree builder, so I can have the left side not conflict with the right side because these are mutually exclusive. But I'm doing something really weird. And that really weird thing is, this is my dependent type. My TB, my dependent type. But this aux is there to hint to the compiler what my dependent type is. So I'm telling the compiler that my dependent type is this thing which is my dependent type. And this works. And if I don't do this, the compiler is just going to lose it. So it's sort of paradoxical that I have to redefine things in terms of themselves. Here's half of the proof. You guys can probably do the other half. You can do that for homework or whatever. Same way. I mean, here's my apply. Essentially is my apply. Is it not? Here's my diff aux. Here's my less than or equal to. When aux coming out, I'm doing height. Same way as I did before, and I'm just redoing my branch. So I have taken this proof and just moved it to a slightly different location, but I'm still forcing you to only create the branch by going through the apply up there, which depends upon this implicit. And the takeaway is, first of all, look, if you screw up your proof, your compiler is going to assert that that screwed up proof has to be true. If you make a proof that can't possibly be true, well, that's your problem. You get to figure this out. Having less than or equal to on the right side or the left side, both of these guys can happen, but they're sort of exclusive. So I can only have on the right side, I can only have on the left side. I can't place these at the same level because type erasure might kick in or something else might happen. So I sometimes need to use a secondary trait to nest my proofs in there. And finally, you know, again, I need to use a type refinement. And I can lose types. Types just, they seemingly disappear with dependent types. You have to keep reestablishing them and hinting the compiler along and going. So do I have any questions? Does anybody want to see anything again? Need a walkthrough? Need an explanation? No. Not at all. Oh, you got to the end. All right. So, as you asked before, there are compile time costs. These compile time costs only come in when I'm recursing. So that thing which is a future, you pay nothing for that. Same thing as you would in any old implicit. You get that for free. That's probably, if you're going to use dependent types, the one you want to use. That type of thing. That's how it fits in. Those things in the standard library, that's how they work too. So use them. They're great. They recapture those types, that any sort of type erasure, you can get it back. Again, if you are recursing, there are runtime costs too. Look, at each step that I recursed, I generated an implicit. And I'm going to do that at each and every step of the way, every time I call this up. So if you have something in a really tight loop, you're going to create an object for each step of that implicit recursion at each time you loop over to. So you can see some really bad GC pressure. And finally, those proofs are programs. But you can't write a unit test. It either compiles or it doesn't. And only later on can you sort of figure out that, oh, hey, I must have goofed that one up because that shouldn't have happened. Sort of. And there's a way to actually test these using macros, but that's way beyond this talk, in a land that I really don't understand quite well. All right. Go for it. I'll go back to any slide. Yes?
So, final thoughts. So, compile time first. Okay, we can make coffee, but runtime is much worse, right?
So, runtime versus compile time costs for these things. So
you said like garbage collection.
So
how you do
that is future thing. Like any implicit that I call, like if I'm using an implicit anywhere and I have to create it, like, you know, on the fly, just one implicit, there's not much cost in runtime. If I'm doing a recursive thing, yeah, that's where you start seeing like some additional stuff come out. Like you might see like, oh, I had to calculate 20 of these. Those nats that I show you, that power, that multiply, that divide, Miles has got that set up such that it works via recursion. So if you have a 20 subtracting, 1, there's going to be 19 objects created for that, plus the top one, which gives you the final answer. And if you have that with that sort of less than or equal to as well, you can see how these things start adding up. So your proofs can actually start really generating a lot of stuff. As a matter of fact, if, my suggestion, if you start doing this, if there's something that you don't know and you want the compiler to come and help you and like come back and say like, okay, you were correct or you are not correct, get it, code it up, get it working, figure out where your bugs were, and then take it out. Really, if it's correct at that point, you don't need these types to help you. You might need them back later, or you might need to put them back in like when somebody else comes along and screws it up, but right then just get rid of them. Yes? Any others? Okay.
Could you maybe go back to the old pattern and let go a bit more of an intuition to exactly what's going on there? Is this, there's a relationship there between type parameters and type parameters, and what is guiding and basic resolution?
Here we go. Awesome. So what is guiding this resolution? This part?
Yeah, you mentioned isomorphism. Yeah, I didn't fully appreciate that.
So this is essentially, these are an alias, like as you're saying, isomorphism. In isolation here. So there's a sort of caveat here. This in isolation, with none of my proofs or anything else that I might be doing, I can express all the types here. I mean, yeah, I could actually plug things in that could never actually truly be. But here, this f of a, and f. This, the way I've done this, because it's w of x to f of x, this is one-to-one and onto. In other words, there's one here, there's one here, there's one here, they map, and it's complete. Like, each of these mappings is onto every single type. So it's invertible. I can go this way, or I can go this way with capturing my types. So even though these are dependent types, you know, these things that I might have to do dot to get back to it, I can pull them out here through this isomorphism. I get this. Now, if this were, shall we say, int here or something like that, or like f of int and kinds of that kind of stuff, then I screw up the isomorphism. Because like then I can't really and truly go certain ways. Like if this is just like, oh, I'm going to be int, like here's w of x, like great, this could be anything because this is a constant and it doesn't matter. So yes, you kind of have to be careful how you write this out so that you can write it out in a way which keeps back and forth going so that it is or does remain isomorphic, but this is essentially an equation. Like think of it like an equation. These are your three variables, and this is your equation around it, and your variables go in here. Yes? What's that? You need to meditate on that. Awesome, cool.
So you have that. Why you have to have this?
What's that?
Why you have to have this?
Why do I need to have this? Because I want to pull these out. I want to have access to these at the same implicit level as here, so that I can put constraints on these dependent types, so I can use these dependent types to constrain the rest of the thing, because that's how I go about like my proofs and things like that. I want to have this, or I need this to work with these types in these parentheses. Have you ever see like things like f of a around the parentheses, and then you have like a over here? That's because the type inferencing works this way. It can't actually work like here and all this other stuff. It just sort of works this way. So here I get to reuse that stuff.
Does that mean that you could, in theory, write up the actual apart, but just with the hashes in there?
I'm sorry, what?
Could you, in theory, write up the actual apart trait, but just with hashes and a bunch of other...
Could I write the apart trait just with like hashes and
instead of using the type alias.
Instead of using the type alias. So no, I couldn't. I don't have those types right here. I have this type thing here, but I really can't. It won't know what it is. It'll just sort of.
So
maybe it will. Like I haven't seen it, but what I have seen is Scala look at this and just go, what do you got here? I don't know. I think actually someone else. Did you? Keep thinking about the type arguments versus dependent types.
Yeah, I kind of see this as just a pattern to make those two complement each other. Like
So a pattern to make them complement each other, yeah.
And in some cases like this, you use the type arguments in order to resolve like these instances.
So sometimes you need to type arguments to get those implicit instances, yes. Sorry, I'm repeating so these guys know.
Yeah. But in order to get like the actual types, you need kind of easier access to the types.
Yeah, to get those types, you need easier access to types, and this complements it, right? Yeah. Yeah. I mean, it sort of is. You're yeah, exactly.
Sorry, I was trying to figure out, when you say you don't have access to the types, are you referring to thing A and F, or what are you referring to you don't have access to types of?
So if I have a part here, this variable, how would I get to this A parameter here? I'd have to do a part.t right here.
Okay.
And if you try and do that, you'll get a compilation error.
Because the part doesn't know what a part is yet.
Yeah, I mean, something, I don't know why, but you get a compilation error.
Okay.
But like this, you don't.
Yeah.
And now you have those types, and you can work with them and plug them here.
Okay.
Isn't it because there's existential or something like that?
Isn't there something about existential? Yeah, I don't know. Sorry, believe it or not, I'm giving this talk, but I really like the type system of Scala is so complex. Like, I can talk to you about this stuff, but like, if you need to do like type level calculations, if Miles gives another like shapeless demo or something like that, like a workshop, a full day workshop, he'll go over that stuff. Go to it, cause like he'll show you this kind of stuff, and like your mind will just explode. You'll walk out like dizzy, like you don't even know what the hell's happening.
So I don't know if you could say a little bit about how the dependent type in Scala works compared to, say, Idris or...
So a dependent type in Scala versus dependent type in like Idris and that kind of stuff. So I can do way more things with a dependent type in Idris than I could in Scala in many cases, or much more easily. So here I have to use the type system, and I have to use like, like you hear things like piano numerals or like church numerals and that kind of stuff, like these like types that I have to build up and work with. So I kind of have to make like artificial representations of the things that I want. So an independently typed language, I can actually come out and say like, this type is going to be a string as long as it starts with the letters foo, F-O-O. And I can actually enforce that at compile time, and it will know, and it'll be like, oh, these are the foo strings, because they all start with foo. I don't know if I can do that here, because then I need to actually pass between the type level and the value level, which Idris allows you to do. Scala, not so much. You're kind of stuck at the type level. You can massage and sort of push your way into it, but that's where the limitations are. You get a lot of flexibility out of Idris. You don't so much out of Scala. But we got them, and this is how we can use them. So, anybody else?
One more thing.
One more thing.
Just how practical is this? I mean, like, you look at it, and it looks somewhat convoluted. I'm just wondering, I mean, I actually see it with use of J-Bless. I mean, it's used in Parboil too, and that's actually very useful, but otherwise I haven't exactly seen any use that I found, wow, this is super cool.
So, all right, so you want to know, like, is this actually practical to use and that sort of thing? It depends. No, I'm going to be, I'll be honest. I showed you a balanced tree. I mean, let's face it, you can write unit tests for a balanced tree, that sort of thing, like an AVL tree. You don't need the types to enforce it. It's a nice, easy example I can show you guys, and like, it's digestible and that sort of thing. There are sort of things that you can program at the type level, sort of tricky things that maybe it's easy to get wrong. That's where it's useful. Miles actually had a great talk at where he was working with the guy from Idris, and he showed like, hey, I can write types such that if a file gets open, or if I grab something like that, some sort of stream, that I compile time verify that stream was closed, that I don't forget to close it. That's where that practical level starts coming in, where you start like using the compiler to sort of enforce things for you, and it sort of works out that way. I mean, God knows how many times I've left things open and not closed them, and then had to pay the price. All right. Well, that's that. Great. Wonderful.